Welcome to AI Paper Podcasts. Today, we're diving deep into a really fascinating piece of research. It throws a significant curveball at one of the most fundamental tools in AI vector embeddings.
Yeah, it's a big one.
Absolutely. So if you're working with retrieval systems, maybe relying on these embeddings day to day, this deep dive is, well, pretty essential listening, I think.
We're looking on the theoretical limitations of embedding-based retrieval. It's work from researchers at Google DeepMind and Johns Hopkins University.
And the core challenge, the big takeaway here, it's pretty profound.
Yeah.
It basically questions this common assumption that, any retrieval problem, no matter how complex, can eventually be solved by single vector embeddings. Just, throw enough data or a bigger model at it.
Right. That's been the feeling. But this paper demonstrates a fundamental, a theoretical limit.
Okay.
They show that even for surprisingly simple queries, in realistic setups, there are specific combinations of relevant documents. Well, single vector embeddings just cannot represent them.
Cannot, regardless of training.
Doesn't matter how well they're trained, how big the model gets, it's a geometric constraint. It's intrinsically tied to the embedding dimension itself.
Wow, and this isn't just like abstract math, is it? They actually built something.
Exactly. They constructed a data set called LIMIT. And what it does is it makes state-of-the-art models fail. Spectacularly fail on a task that seems ridiculously simple.
Okay, that definitely gets your attention.
Yeah. And it points to this really critical need, maybe, for new architectural approaches.
Yeah.
Something beyond just single vectors.
Okay, let's unpack this a bit more then. For years now, information retrieval, it's been heavily dominated by neural language models using these single vector embeddings, right? Dense retrieval.
That's right, dense retrieval. We've seen incredible progress. We've moved way beyond the older sparse techniques like EM25.
Keyword matching, basically.
Yes, exactly. To models now that can do really sophisticated things, understanding complex queries, nuances. It's felt like this sort of unstoppable march forward.
Embeddings just getting better and better, handling more complexity.
Absolutely. These models have been pushed, to generalize across huge data sets, tackle increasingly intricate problems. Think about instruction following benchmarks like Quest.
Right, where they combine concepts, use logical operators.
Exactly. Like finding moths or insects or arthropods of Guadeloupe. Or look at Bright, which needs actual reasoning to find related leak code problems.
Okay.
So the implicit assumption, maybe unspoken sometimes in the community, has been, that these embeddings can handle pretty much any relevance definition for any query you throw at them.
We're in this expanding universe of dense retrieval, thinking the sky's the limit.
Pretty much.
So while everyone's pushing the boundaries of what embeddings can do, this paper takes a step back. It's like they're asking, okay, before we build this skyscraper higher, is the foundation actually solid everywhere?
That's a great way to put it.
Are there inherent limits, things that even the best models just can't escape because of the geometry of the space they live in?
Yes, exactly that. And what's really fascinating is how they connect things. They bridge known theoretical results from communication complexity theory.
Okay, that sounds pretty theoretical.
It is, but it's relevant. Communication complexity looks at how much information two parties need to exchange to compute something together. They use this framework to establish a fundamental lower bound.
A lower bound on what?
On the embedding dimension, you need to accurately represent a given set of relevant documents for a set of queries. It's a really neat bridge between pure theory and, practical AI retrieval.
So let me see if I get this. They're saying the actual space, the vector space where embeddings live, it has rules, constraints. It can only hold so much complexity.
Precisely. That's the core idea. They formalize this using a concept called the sign rank of the query relevance matrix. They call it the qrel matrix.
Like a big table of what's relevant to what.
Exactly. Think of it like that. Rows are queries, columns are documents. A 1 means relevant, 0 means not relevant. The sign rank, then, basically tells you how many distinct fundamental patterns of relevance are in that matrix. And crucially, the higher that sign rank,
the more dimensions you need in your embedding?
Bingo. The higher the sign rank, the higher the minimum embedding dimension D needs to be to even have a chance of capturing all those unique relationships. Specifically, they're related to the sign rank of a derived matrix, 2A1.
Okay, the math is getting a bit deep, but what does a high sign rank mean conceptually? Like, what kind of retrieval task would have that? Is it finding things that are only relevant in weird combinations?
That's a good intuition, yeah. A high sign rank suggests the relevance isn't simple. You can't just draw easy lines in a low-dimensional space to separate relevant from irrelevant. It means that these intricate combinatorial patterns, you need more independent axes, more dimensions to tell them apart. So for any fixed dimension D, there's always some relevance pattern, some binary matrix that D dimensions just can't handle.
No matter what.
No matter what. Tasks with these high sign rank qrels are just fundamentally harder for single vector models. And it's not something you fix with more data or tweaking the training. It's structural. Baked in. It's structural. The model's geometric space just isn't big enough, doesn't have enough room for all the combinations.
That is a profound claim. So how do you prove something like that isn't just, hard training, but actually impossible? They use this free embedding optimization.
They did. And it's a really strong argument. They basically said, let's remove all the complications of language. Let's give the embeddings the absolute best possible chance.
Oh.
They directly optimized the query and document vectors using gradient descent. The vectors should basically move anywhere to find the perfect configuration. No constraints from words, just pure vectors finding their ideal spots.
The absolute best case scenario.
The absolute best.
Yeah.
If this setup fails, then any real-world model with all the messiness of language and training is definitely going to struggle, right?
Makes sense.
And they optimize directly on the test set using info-NC loss.
Right, the loss function that pushes relevant pairs together and irrelevant ones apart.
Exactly. So they gave the embeddings every advantage, a perfect setup. Then they started adding more documents.
Until it broke. Until it couldn't get 100% accuracy anymore.
Precisely. They call that point critical N. The number of documents where the system just couldn't perfectly represent all the required relevance relationships anymore.
And what do they find?
For the case with K2, relevant documents per query, which is pretty common.
Yeah, like in standard benchmarks.
Right. They found this really clear polynomial relationship between the embedding dimension D and this critical N point. They even give the formula. It fits incredibly well.
Y equals 10.5322 plus 4.0309 ds, something like that.
Yeah, plot terms for D squared and D cubed. The fit was almost perfect, R squared of 0.999.
Okay, so there's a mathematical relationship. What's the implication?
The startling implication comes when you extrapolate, even if you push the embedding dimension up to something huge, like 4D96.
Which is massive in practice.
Massive. Computationally very expensive. Even then, the number of documents whose combinations you can perfectly represent, it caps out around 250 million.
250 million sounds like a lot, but...
But for WebScale Search, billions of documents. It's just not enough capacity to model all the potential combinations, especially the tricky ones. It's just a hard limit.
A physical limit, almost, on the representational power. Okay, that's compelling from the theoretical best case side. But does this wall actually show up with real models, real language? That's where the LIMIT Dataset comes in.
Exactly. LIMIT is designed to be the bridge. It's realistic, uses natural language, but it's also built specifically to be, well, trivially simple in concept, yet demanding in terms of this combinatorial representation.
How did they build it?
They mapped combinations of documents to simple attributes, like imagine a query who likes apples and quokkas.
Okay. Specific combination.
Right. And a document might say, John Durbin likes quokkas and apples. Another might say Sarah Bell likes peaches and grapes. The relevance isn't just apples or quokkas, but the combination. They made sure the preferences were consistent too. Like, you could like Hawaiian pizza, but not pepperoni.
Got it. So it forces the model to understand the A and D.
Precisely. It forces that combinatorial understanding. They used a corpus of 50,000 documents, 1,000 queries, again with K2 relevant docs per query, similar to things like InQ or Hotpot QA setups.
Okay, standard-ish setup, but with this combinatorial twist. So, the moment of truth. How did the big state-of-the-art embedding models do? The ones we use every day.
The results were...
Well...
revealing is an understatement. They struggled. Bad.
Like how badly?
Models like GridLM, Qwen3 embeddings, PromptReavers, Gemini embeddings, Snowflake Arctic Embed, E5 Mistral Instruct. These are strong models.
Yeah, it's top-tier stuff.
On the full LIMIT dataset, many couldn't even get 20% recall at 100.
Recall at 100. So out of the top 100 results, they couldn't even find one of the two correct documents 80% of the time.
Often, yes. And maybe even more telling. They created a tiny version, LIMIT Small, with only 46 documents.
46? That's minuscule.
Tiny. Even on that, These powerful models still couldn't reliably solve it, often getting recall at 20%. It really drives home this idea of a representational bottleneck.
That's honestly astonishing. Models that handle complex reasoning questions failing on who likes apples and quokkas with only 46 documents to check. It makes you wonder, is it just some weird domain shift? Maybe they just haven't seen data structured exactly like this?
That's the obvious question, right? And they tested it carefully.
Yeah.
It's not just domain shift. They took an off-the-shelf model, fine-tuned it on an in-domain limit training set.
So showed it examples of this exact task structure.
Exactly. And the improvement was minimal, like maybe going from near 0 to 2.8% recall at 10 for a 1024 dimension model. It helped a tiny bit, but didn't solve the fundamental problem.
So it's not about familiarity with the content.
No. It really points back to the model's core representational capacity. But here's the kicker, echoing the free embedding results. If they train the model directly on the test set,
just let it overfit like crazy.
yes, then it can solve the small version, which again strongly suggests the bottleneck is representation, not training or domain. The model can memorize the answers if forced, but the embedding structure itself struggles to represent the relationships generally.
Wow. And they also found that the structure of the relevance patterns in LIMIT mattered, this dense qrel pattern.
Yeah, they measured things like graph density and average query strength. LIMIT was designed to maximize these combinatorial requirements, creating a very dense pattern of interconnections. And they show this dense pattern was significantly harder than other sparser relevance patterns they tested. The way combinations are structured really dictates the difficulty.
Okay, so the evidence seems pretty strong. Single vector embeddings, even the best ones, hit this fundamental wall because of their dimensionality when faced with certain combinatorial relevance patterns. So where do we go? What are the alternatives if we need to capture this stuff?
That's the critical question, and the paper explores a few key architectural alternatives. First up, cross-encoders.
Okay, the ones that look at the query and document together. Usually used for re-ranking because they're slow.
Exactly. They're computationally expensive for first-stage retrieval. You can't pre-compute document vectors. But state-of-the-art re-rankers, like Gemini 2.5 Pro, they tested it. It perfectly solved the limit small task, 100% accuracy.
Whoa, from less than 20% recall to 100%.
Yep, because they don't rely on that single pre-computed vector similarity. They look at the full interaction, the combination of features dynamically. They bypass that geometric bottleneck.
It shows the information is graspable, just not by a single vector comparison. Okay, what else?
Then there are multi-vector models. Think
Yeah.
Colbert, or the GTE modern Colbert they tested.
Right, where each document or query is represented by multiple vectors, not just one.
Exactly. They use multiple vectors per sequence, often combined with something like a maxim operator to find the best matching part. And these showed greatly improved performance on limit compared to single vector models.
Better, but not perfect like the cross-encoder.
Not perfect, no, but significantly better. By using multiple vectors, you're essentially giving the representation more dimensions, more ways to capture those combinatorial nuances. It raises interesting questions about how far you can push this for more complex reasoning tasks.
And what about going back in time? Sparse models, BM25.
Interestingly, yes. Sparse models, like good old BM25, actually performed very well on limit, close to perfect scores.
How? Why do they avoid this problem?
It's all about dimensionality, in a sense. Instead of a few hundred or maybe a couple thousand dimensions like dense embeddings, sparse models effectively operate in a space with potentially millions of dimensions, one for each term in the vocabulary. This massive dimensionality gives them way more capacity to handle combinations. They sidestep the low-dimensional bottleneck.
But the trade-off there is they struggle with conceptual matching, right? If the words don't overlap.
That's the main challenge. Applying them effectively to abstract instructions or reasoning where there isn't that direct keyword overlap is hard. Canine companions versus dogs, dense embeddings excel there.
So it really highlights this fundamental trade-off. Single vector embeddings, efficient, great generalization for many conceptual tasks. But they hit a hard ceiling on representing all possible relevance combinations.
Precisely. It's a capacity issue inherent in the low-dimensional structure, not just a need for better training. It really forces you to think about whether that efficiency is always worth its theoretical limitation, especially as retrieval tasks get more complex.
This whole deep dive on the theoretical limitations of embedding-based retrieval It really does make you rethink some core assumptions about modern retrieval, doesn't it?
It really does.
It suggests it's not just about making our current single-vector models incrementally better with more data or slightly bigger sizes. There are inherent theoretical limits we might be running up against.
Exactly. And that raises a crucial insight, maybe a question for you, the listener, as you're designing or thinking about retrieval systems.
Yeah.
As the demands keep growing, needing highly specific instruction following, more nuanced reasoning, find these really precise combinations of information. Our single-vector embedding is going to remain the default choice for that first retrieval stage.
Or do we need something more?
Or will we see, maybe need to see, a significant shift towards more expressive architectures, multi-vector, perhaps hybrid sparse dense approaches, maybe even clever ways to integrate cross-encoder-like interactions earlier. Architectures that can fundamentally overcome these representational bottlenecks.
So it's a call to think about architecture with these theoretical boundaries in mind, not just chasing the next few percentage points on a benchmark with the same old tools.
I think that's a fair summary. Being aware of the limits is key.
Definitely something to chew on as you build your next retrieval system. We really hope this episode has given you some valuable and maybe provocative insights. Thanks for joining us on AI Paper Podcasts.